Welcome to the What's New presentation for MDA version 8.7.3. My name is Matthias Gekeler. At ETAS I'm the Product Manager for MDA. In the present video I'm going to demonstrate the new features and improvements listed here. In the description below the video you can find the corresponding jump marks. First, I'd like to demonstrate a new instrument. So far you can see in an oscilloscope the signal curve along the time. The statistics instrument provides, for example, the minimum and maximum values of the signal. To get more information about the samples distribution of the signal, the histogram instrument is introduced. This instrument conducts a classification of all samples for the time range defined in the time slider bar. As usual, also the histogram supports the synchronization with other instruments in MDA. So, you can define in an oscilloscope the relevant time range, and the data in the histogram gets updated. When the time range is changed, the update happens just after the mouse is released. My current example signal was recorded in a 1 millisecond time raster. Thus, it comprises in total about 5 million samples. The reclassification happens pretty fast. Here is another even more challenging example signal. It was recorded in a 100 microseconds time raster. You can replace the former signal in the histogram just by dragging and dropping of the new signal. For my new example signal, roughly 50 million samples need to be processed. In my opinion, the time it takes to show the results is not too bad. Obviously, the defined classes in the histogram do not fit to the values of the new signal. Therefore, a colored bucket is shown. This indicates to you that there are samples which are exceeding the defined overall value range for all classes. In the statistics instrument, the minimum and maximum values can be seen. These can be used to set more reasonable properties for the histogram. The properties include the number of buckets, the interval size, which means the width of each bucket, and the center value for the first bucket. If all samples fit into one of the defined buckets, the colored bucket for extreme outliers disappears automatically. Also for the statistics instrument, some functional enhancements were implemented. Some additional columns for the statistics instrument are available. From the list displayed by the Show Hide icon, these can be selected. There are several new entries. One is to display for each signal the ECU meta information. As usual, a change in the list is reflected directly in the instrument itself. As new statistical value, the median calculation is offered. The median represents the value which splits the samples into two groups with the same number of elements. In contrast to the average or mean value, the median is not affected by extreme small or large sample values. Thus, depending on your use case, the median might be more meaningful than the average. Moreover, two further columns are listed. These will show the minimum, respectively the maximum values, but in decimal representation of the raw value. Both are introduced together with the support of enumeration signals in the statistics instrument. For enumerations, a verbal value is defined by the conversion formula. In the columns for the minimum and maximum values, these verbal values are shown. The corresponding columns with the decimal values help to better classify the further statistical values like average and so on. For enumerations, these statistical values are also based on the decimal values of the samples. For ordinary numerical signals, the physical values are shown for the statistics. The shown data comprises all samples of the time range defined in the time slider bar of the instrument. Synchronization with other instruments is supported, so you can directly zoom in to the relevant time range in an oscilloscope. The data in the statistics instrument is updated accordingly. Finally, you might want to reuse the shown statistical data in another application. To do so, simply select the desired signal rows. Then open the context menu and use the entry Copy Contents. The data is now available in the Windows clipboard, so you can paste it into the desired target location. The contents include the instrument's column header and the data of the displayed columns. This allows to get for enumeration signals the verbal minimum and maximum values, as well as the decimal values for the other statistical columns. The next topic is about a basic enhancement for the support of ASCII-based measurement files. Already since 2018, MDA offers an interface to define your own ASCII-based measurement file formats. The advantage of this approach is that you need to define your specific format only once. Afterwards, such files can be added to MDA without further import steps. Also, the export of measure data into your defined formats is possible. And the defined file formats are also supported in the command line tool mdf-convert-exe. How to define the respective INI file is explained in the example ASCII format INI file. It is provided with the MDA installation. Therein, all options are described in detail. But so far, each INI file could include only one structure for one file extension. Now I want to show how to support different variants of files having the same file extension. To do so, I have prepared some example files. These include the same signals and data, but are structured differently. In the first variant, just the pure signal name is given. For the definition of a variant, also the name of the time channel is important. The second variant has a different time channel name. Moreover, it includes a row for the signal's unit information. In the third variant, also a row with device information is given. And the last example variant combines signal name, device and unit information in one row. To support all of these CSV variants, a new INI file must be created. Together with the installation of MDA, a new example file is provided. It describes how to combine definitions for multiple variants of the same file extension. The possible options for each variant are the same as for the individual INI files. Based on the new example file, I have created my multi-CSV INI file. Important is that there must be a section named Common. It includes the definitions which are valid for all the variants defined below. So the Common section includes at least the file extension. For my example of files with comma-separated values, also the comma is the common delimiter in all variants. Below the Common section, the specifics of the different variants are listed. When creating an INI file, it is important to know that these definitions are applied one after the other. As soon as a definition can be used to load a file without contradictions, it will be used. Then the following definitions will not be tried anymore. Therefore, the list should start with the very specific variants. The more general definitions should follow subsequently. The best criterion for a clear identification of a variant is a unique name of the time channel, while the information in which row the data starts is rather unspecific. Additionally, you should use speaking names for each variant, since you can see these names later in MDA. The INI file must be stored in a subfolder of the ASCII configurables. But all files which are located in the Examples folder will be ignored. After having added or changed an INI file, a restart of MDA is required. Then the new file definitions will be used to load measurement files. I start with my example file, which includes only the signal name. The signals are identified correctly and can be used as usual. In the table instrument, you can see that the time channel is also interpreted correctly. It starts at 0 and the next timestamp is at 0.053. Exactly as in the CSV file. Now I'm adding all the other example files to check whether the definitions given in the INI file are applied correctly. It is obvious that the timestamps and the signal values are identical. Also, the different degrees of meta information for the files are handled as expected. This means that file number 2 includes the unit information, while for signals from the files number 3 and 4 also the device information is given. If the result was not as desired, you should check whether a different order of the file specifications in your INI file solves the problem. And eventually, the defined format variants can also be used for the export of measurement data from MDA. The names given in the variant sections of the INI file appear as new entries in the file format drop-down selection list. Another enhancement relates to the support of CAN bus trace files. CAN bus trace files in BLF and ASCII formats can be loaded already. Now also the MDF file format is supported. You can select it as any other of the supported CAN bus trace formats. For the interpretation of the trace file, a description file needs to be defined. And additionally, the CAN bus ID, respectively a CAN node, must be assigned. Finally, an AFF file entry appears in the File Explorer as a reference for the combination. As usual, the basic trace signals are listed in the Variable Explorer. These can be displayed, for example, in a table instrument. With a correctly added description file, also signals are interpreted out of the trace data. This is the same behavior as for the other CAN bus trace file formats. But there are two special aspects which should be mentioned for MDF files which include CAN bus trace data. Typically, MDF files are loaded via the icon for adding an ordinary measurement file. If this is done, then only the signals will appear in the Variable Explorer, which are available in the MDF file. So far, it is not possible in MDA to combine an MDF file loaded as an ordinary measurement file with a CAN bus description file. This means that from the CAN bus trace data, only the basic CAN signals will be listed, but not the interpreted signals. And the second special case is that in some specific MDF files, the interpreted signals from the CAN bus trace data might be available already. This depends on the application used for the recording of the MDF file. Also, the support for parameters from calibration data exchange files was extended. Calibration data exchange files in CDF formats include calibration data for parameters like values, curves or maps. So far, a curve or map can be assigned to a calculated signal using a lookup table functionality. In my example, the CDF file contains only values. These represent just constants. As always, CDF files contain only data, but no raster or timestamp information. But when assigning a value from a CDF file to a table instrument, a virtual timestamp will be shown. This virtual timestamp will always appear as the first entry in a table. The value of the timestamp is defined by the assigned measurement files and optionally time offsets. Value parameters from a CDF file can also be assigned to an oscilloscope. So the value can be used as a comparison line for an ordinary signal from a measurement file. Preferably, you assign both to the same axis so that their curves will be moved together when scrolling or zooming the value axis. Since the constant value has no timestamps, it covers always the complete visible time range. A value parameter can also be used as constant in calculated signals. This might be used, for example, to identify points in time at which a measurement signal exceeds the constant value. There is one special case I'd like to mention. If a value parameter from a CDF file is used without any measurement signal, it will not automatically provide a valid calculated signal. This behavior is indicated by the error symbol. The tooltip explains what needs to be done. Just assign a fixed output raster for the calculation, and then the calculated signal can be used. In this final section, I will show another generalization for the so-called battery instruments. As last possible adaptation, a definition of the imbalance unit was missing. In case the cell voltages of your battery system were recorded in the unit millivolt, you probably also want to see the imbalance values in millivolt. As usual, such an adaptation can be done in the properties of the instrument. There are fields in which you can define the desired unit for the input signals as well as for the imbalance values. To obtain a consistent calculation of the imbalance values, you should also think about the conversion between the units. Any changes are applied directly to the instrument. Moreover, the last defined settings are used as default for any newly created battery instrument. Since any battery instrument can display only one specific point in time, the synchronization feature is important. It allows to navigate the cursor in an oscilloscope to a relevant point in time. For exactly this new point in time, the views are updated immediately. Thus, you can see directly the new signal distribution in the battery histogram and the corresponding imbalance values in the graph instrument. The instruments are also suited to display other signals than battery voltages. In the next example, I have chosen some temperature signals. Therefore, I change the unit for the input signal to degrees Celsius and for the imbalance to Kelvin. The conversion factor between both units is 1:1. Moreover, it is possible to adapt the information shown in the instrument summary area. This includes which entries shall be shown or hidden in the summary area. Also, the displayed names can be defined. And for each entry, the number of decimals can be set. Finally, you see here the overview of all changes done in MDA version 8.7.3. For more details, please have a look into the What's New slide set. You can find it, as well as further information materials, both directly in MDA 8 as well as on the ETAS homepage. Thank you for your attention and for your interest in MDA 8.